Hi everybody. Today I'll be talking about chemical reaction engineering. This is basically a shortcut video as always because I love shorts. This is a shortcut to remembering all the important formulas that you need for any kind of competitive exams where you're appearing for this particular subject. Now this has never been my favorite subject, so I try to grasp only the important formulas that I cannot do without at all in any kind of competitive exams for this subject. Okay, so if you are an extensive reader, please do not watch this video. Refer to your books, read well. And as for those who are preferring shortcuts or a last minute revision of all the important formulas, you can go through this video. First thing to mention, I hope you all have this basic idea of chemical reaction engineering, what this subject is about. It's about reactors, it's about a reaction, how it is occurring, what kind of reactor I must use for what kind of influences temperature or pressure have on it, etc. So first thing you need to know about this subject is its first most important formula that's written in the first page of every chemical reaction engineering books. That is this: Ca equals to Na by V. What are all this? Ca is concentration of our species A, okay, and Na is the number of moles of A that we have at hand, and V being the volume occupied by A. So what we get is Ca is a ratio of the number of moles of A and the volume occupied by it. So it's basically moles per unit volume. Okay, this is my first formula. Next, I'll tell a relation. Suppose you get any kind of question where you are said that you know the equilibrium constant for a particular chemical reaction with respect to its concentration, and you have to calculate the equilibrium constant with respect to partial pressure for the same. How do you do that? So Kc be that thing for equilibrium constant for concentration equals to equilibrium constant for partial pressure multiplied by RT to the power capital N, where capital N is the total number of moles of the reaction species and R is my universal gas constant, of course. T is the temperature. Please use scale, okay? When you are with this universal gas constant, please be careful of the unit that you are using. Accordingly adjust the temperature, right? It's very important because silly errors occur due to that. Next will be another formula. Say a particular species A has reacted to give me products, okay? A particular species A has reacted to give me products. I do not know the order of reaction. I do not want to know it right now. But during this particular reaction, the conversion A, that means the amount of A that has been consumed by the reaction to produce these products, let it be denoted by XA, where XA is my conversion of A. Then what is the amount of A that is remaining with me? Okay, so that is given by Ca equals to Ca0 into 1 minus Xa. Okay, what does it mean? Ca0 is basically your concentration of A at time 0 equals to Ca0, and Ca at time, say x or anything, say at time t, okay, equals to Ca, right? And Xa is your conversion of A. So the amount of A that is left with you is given by this, right? Okay. Next, say you are supposed to calculate the heat of a reaction. Heat of reaction, product side minus heat reactant side. Okay, heat of reaction equals to heat on product side minus on reactant side. This is for any kind of chemical reaction. In case you have one known, in case you have two known, you can calculate the one unknown.